Okay. I was looking at the schedule. Um, we actually don't have enough to fill a full semester. So once we get to a point, it's like, we're done. As far as class meetings are concerned. So, after today, there's a couple more topics related to eigenvalue problems. Then I have a couple, but very much tiptoeing into statistical learning and pointing out, overlap with numerical linear algebra. And there's just gonna be an online quiz on that stuff. And then I don't have anything else, although I have one class period set aside for, um, it's labeled coding project discussion, but that's only relevant if anyone here, is planning to do the coding option for homework 4. So homework 4, there's like a regular assignment, explorations from a textbook like the other ones. Or there's, uh, uh, one involving, coding up the symmetric QR algorithm, which is what I'll cover next time. Um, and, and if there's some parts of it that are pretty challenging, so I would just, set aside some time for that, if anybody's doing it. So, what? You are? Okay. And you?
Probably.
Oh, okay.
I'm gonna suck pretty hard at the coding on this. Last homework.
Oh, okay.
Thank you. I plan on trying it.
Okay, well, there's a fair amount of guidance too, like, because there's some pseudocode from Golub and Van Loan, that would, be included, well, pseudocode only goes so far, especially when it comes to things like loops and such, so.
What's it been a couple months, but I think since 7/21 I took with you, like doing the code just helps me understand the math better for some reason.
Yeah, I can see that. Okay. All right, well, then that's what we'll do during that class period, which is, I think, well, it might be next week, I don't remember, doesn't matter. It's coming sometime. Oh, what over here? Oh, Bill is here. Okay. That's totally false. Yeah. Um, yeah, your brain's working very different ways for math versus code.
Maybe honestly, I was relevant in a way, so it was helping me. I was like, I see.
Yeah. Okay.
Good one, that you did.
Sorry, what?
The one that you just did, like.
Oh, okay. I don't know. So I was distracted, so I didn't catch all of that anyway, so, yeah. Um, okay, so that's good to know about, who does what for homework 4. Um, okay, so, like I said, it's gonna be on, uh, symmetric QR algorithm, but it's for next time, but, today is when I finally, arrived at the general algorithm for that's reasonably efficient for the most general unsymmetric eigenvalue problem. Okay, so. Okay. Um. So. So where we're at right now. So we want A be decomposed, where A is real. And we want to arrive at its real third form. And the algorithm we have up to this point is, we apply household reflections to A on left and right to reduce H to Hessenberg form. And then we have our iteration where we apply QR iteration to H. So we perform the QR factorization of H, and then we overwrite H with the Q and R factors multiplied in reverse order. And by while not converged, that means we keep going until H is reduced to this quasi upper triangular form where we have only 1 by 1 or 2 by 2 blocks along the diagonal. So one iteration of this now takes only order n squared floating point operations because of H being Hessenberg. We only have to eliminate one subdiagonal entry per column. So by performing Hessenberg reduction, we reduced the work of QR iteration by an order of magnitude. But we still have a problem of convergence being too slow. It takes too many of these iterations. We want to try to cut that down. Right. So if we can somehow quantify how rapidly or how slowly this iteration converges, this will give us an idea of what to do to improve it. So what we know is that a given subdiagonal entry of a peak subdiagonal entry, which we want to go to 0, it goes to 0 at this rate. It depends on the ratio of these eigenvalues, lambda p plus 1 over lambda p. And keep in mind, our convention is that lambda 1 is the largest eigenvalue, so higher index means smaller eigenvalue. So this this ratio is supposed to be less than 1. Well, if it's equal to 1, like if lambda p and lambda p plus 1 are a complex conjugate pair, then that subdiagonal entry is not going to go to 0. That's where we get a 2 by 2 diagonal block. But if these eigenvalues are at least distinct, then we have some kind of convergence happening from this ratio being less than 1. But if the eigenvalues, I think that's a whole, but the certain ones are clustered, then this rate of convergence is nearly 1, and that is what leads to slow convergence. That the that subdiagonal entry that we want to drive to 0, it is going to 0, but taking too long to get there. Okay. So here's what we could do. Suppose we apply a shift. In other words, we try this instead. Instead of QR factorizing H, we shift all the diagonal entries of H by some chosen mu, and we don't know how to choose it yet, but I'll come to that. We QR factorize that, okay. And then the new H, we go ahead and multiply R and Q, and we add the shift back. Okay. So the new H will still have the same eigenvalues as the old one, but the Q and R will be different this time because we're QR factorizing a different matrix from the spectrum shifting. So the new rate will just subtract the shift from both. Okay. So if we can choose a shift mu that will make this, fraction, smaller, then we've accelerated, the convergence. All right. Oh, by the way, it can be shown, if I call this H tilde, the new H, then just like before, you can work this out that the new H is, well, okay, just for fun, just go through the steps. It's RQ plus mu I, but R comes from this Q factorization here. It's Q transpose H minus mu I. Okay, so all this is R times Q plus mu I. But then if you work all this out, the terms involving mu will cancel. And you just get Q transpose HQ. So just like we had before doing any shift, we're still performing a orthogonal similarity transformation of H to get the new H. But hopefully a more advantageous Q than before. So, how should we choose mu to make that fraction as small as possible?
We can make it largest eigenvalue.
Well, for folks at these eigenvalues, the eigenvalues prior to lambda p, we assume those have already been found. Or I guess lambda 1 to lambda p have already been found because we've made certain subdiagonal entry 0, and now we're trying to get, so you can think of lambda p as being known. And this is what we're trying to get. So we'll make a fraction small.
So when I have a small mu, but how would you find the ideal?
Fraction would be smallest if the denominator was largest.
Yeah,
Relative to the numerator.
yeah.
Okay. So,
You know, the one is smaller than one.
yes. Well,
No, but it is.
true, but you actually have hit upon it that, okay, we may not know lambda p plus 1. Yeah, so,
So make it out, lambda p.
yeah, well, no, but yeah, I can't do that. No, but if we can estimate this, then we will be on the right track. So, so that's the ideal situation. That the better estimate of an eigenvalue mu could be, then the faster the convergence will be. But it does, yes, it is a chicken and egg situation. I'm not denying that. But that's still guidance on what we practically can do. Okay, so all right, so oops. We get faster convergence. If mu is approximately equal to lambda p plus 1. Okay. Now, okay. Now, the idea of what's going on here, your factorization. What if mu is equal to an eigenvalue. What would happen if this QRRQ thing? That would mean that H minus mu I is singular. But then if we take the QR factorization of that, and this is the full QR factorization, everything here is a square matrix of the same size, n by n. And since this is singular, this product also has to be singular, but an orthogonal matrix is by definition invertible. R has to be singular. Okay. I forgot to say the assumption here. We'll assume that H is unreduced. All the subdiagonal entries are non-zero. And that's a reasonable assumption because if it's not unreduced, we should be decoupling it anyway. So that it is unreduced. Okay. Now, what I mentioned before about an unreduced Hessenberg matrix is its the first n-1 columns are linearly independent because of a Hessenberg structure. So in fact, I can tell you what the structure of R is. Okay, so it's upper triangular. But the last row is entirely zero. Okay, so knowing that R is singular, that would tell you that at least one of its diagonal entries is zero. That's the only way it can be singular. But because of H being unreduced Hessenberg, we also know which of those diagonal entries is going to be zero. It has to be the last one. And this is true because the columns 1 to up to n-1 of H minus mu identity they have to be linearly independent. Okay. So now that we've done that QR factorization, we have to do this other step here where we do RQ and then we add the shift back. So H tilde is RQ plus mu identity. Now, when I take this R and I multiply by Q on the right, this is a Givens, a product of Givens column rotation because it's being multiplied on the right. Okay. Now, if I'm taking these columns and rotating them, what do we know about the last row of RQ? So forget this part, just focus on RQ. We're rotating columns of this, and that's going to make it Hessenberg again. But what can we say about the last row? What?
It's irrelevant. All zeros.
Yeah, it's still going to be all zeros because I'm taking combinations of entries from these columns, but in the last row, I'm combining nothing but zeros. So, the RQ plus mu I, once I add the shift back in, I'm going to have a Hessenberg matrix, admittedly a crooked one. But this subdiagonal entry, the last subdiagonal entry, will still be zero. And then I'll have mu sitting by itself, lower right corner. So what that means is decoupling. the way that my advisor's textbook, Golden Van Loan phrases it, when you shift by an exact eigenvalue, deflation occurs in one step. When you shift, okay, this is assumption of an unreduced Hessenberg matrix. If you shift by an exact eigenvalue, then deflation occurs in one step. Okay.
In this decoupling, or the only thing that shifts is the velocity,
Wait,
the deflection. When you said deflection,
Yeah.
in one step,
oh, deflation,
deflation.
yeah, okay. Yeah, or you could also describe it as decoupling occurs, so it does one step. Okay, but of course, we can't set mu equal to an eigenvalue. So if mu instead is approximately the next eigenvalue we're looking for, then we can say it's h minus mu I. It's not singular, but is nearly singular. And that tells us that R and N will not be zero, but it will be small. Due to that near singularity. Okay. And what that also tells us is that in the new Hessenberg matrix, H tilde, the last subdiagonal entry will be small, and the last diagonal entry will be approximately, there'll be a better approximation of this eigenvalue. So we shift by an approximate eigenvalue, at least we can make a subdiagonal entry smaller. And if we just repeat this process, make it smaller and smaller still, that's the hope, is that eventually we will be in this ideal situation where, at least within machine precision, decoupling has been achieved. So this takes us to what's called the single shift strategy. And that is following: set mu equal to the NN entry, the lower right entry of our Hessenberg matrix. And then we go ahead through this process. We pure factorize H minus mu identity. And then we overwrite H with the updated matrix. And then repeat the process. We'll get a new shift with the new HNN, which is hopefully closer to an eigenvalue now. And we keep going. And repeat until coupling has been achieved. And then we found n eigenvalues. And now we can work with the rest of the matrix to find the next one, and so on.
Since this will theoretically always get you the decoupling, you would actually just repeat until you get R being R being singular, or it crosses a certain tolerance.
Okay, well, I guess one point to spot is if you do this and you find that RNN is now essentially zero, yeah, then you know it's going to be your last iteration. Yeah, so then you can go ahead and complete the step. Now this new H will be decoupled, and now you can change which block of H you're working on. for subsequent iterations. What?
And zero would be the point where we know that
Yes,
we have achieved.
So this is an iteration inside of it, iteration.
it, well. Okay. You could structure it that way. And I guess you can code it either way, but it's still one main iteration. It's just that what portion of H we're working on changes during the iteration.
Yeah.
To be unreduced. So then you'll have some variables that will monitor to keep track of what block you should be working with. Initially the whole matrix, but then as you peel off eigenvalues, then you're working on smaller blocks. Okay. So what I'm going to do is give you an idea as to how well this works by looking at a 2x2 case. So let's suppose that our Hessenberg matrix, after shifting, as this form, A, B, epsilon, and then 0, where mu was equal to the original H22. So that's why that 2 entry is now 0. Okay. So we're doing QR on this matrix because it's only a 2x2. It's all we have to do is make this entry 0. So all it'll take is a single Gibbons rotation to make that happen. So I go ahead and for my Gibbons rotation, from these elements here, so E is going to be, and we're focusing on the first column. So we're our cosine sine pair come from A and epsilon. Okay. So what happens is the okay. Then G transpose A minus mu identity times G. So we go ahead and carry out the symbolic transformation. What that will give us is right. So we have A, original A, plus this added on. And then we have B C squared minus epsilon, and then we have minus B S squared. And then we have minus B CS. Now, we do need to add the shift back to the diagonal entries. But what I want to focus on is this entry right here. So, and how that subdiagonal entry that we want to make 0, how did it change after performing this transformation? So the subdiagonal entry started out as epsilon and it changed to minus BS squared. But now I'll fill in what S is. So now we have minus B epsilon squared over square root of A squared plus epsilon squared. So, in other words, suppose epsilon's already small. What? Oh, yeah, it is. Yeah. Okay. If epsilon is already small, the new subdiagonal entry is going to be a lot smaller because it's order epsilon squared. Okay. And this is significant because it tells us that convergence is quadratic. Compared to the previous convergence rate, if we use a fixed shift view, this is linear convergence. But because we are changing the shift from one iteration to the next, always getting a better estimate of the eigenvalue, that subdiagonal entry now goes to zero quadratically. And why that's a big deal is that means it only takes order 1 iterations per eigenvalue. You think about, you want this entry to be 0. With quadratic convergence, the number of 0 decimal places roughly doubles from one iteration to the next. So if you're trying to get 50 digits like machine precision to be 0, that can be done in like 4 iterations or 4 or 5 iterations. So there's only a limited amount of work that's needed to peel off one eigenvalue. So to get all the eigenvalues of n by n matrix, you can accomplish it in order n QR iterations. Each iteration takes order n squared work because QR factorizing a Hessenberg matrix. So order n cubed work in total, which we're okay with. I mean, yes, that's expensive, but certainly that's the best we could expect for getting all the eigenvalues of a dense matrix. Okay. All right. Now so a numerical example that I have in the notes. Okay. 2 by 2, but okay, so this subdiagonal entry, we want that to be 0. Right now, it is smaller than the other entries, but not that much smaller. Less than an order of magnitude smaller. So then, if I do a chart of how many iterations I performed and what happens to the absolute value of that subdiagonal entry, and what we get is actually the first entry made slightly bigger. That can happen, unfortunately. Then it gets a little smaller. And then one more time, it's 0.00021. So in the order of 10 to the minus 5. And then we have and then a whole lot smaller. Because we take one more iteration and then it's 0 to machine precision. So we can see in this case, this is what happens. Okay. Just got a thing or waiting for emergency button that's going. Yay. decided to cut all hiring lines that have not yet been completed. So I think we just barely got on for a wire.
Yeah.
Uh,
Mm.
um. Uh, hmm. Yeah, one thing is kind of weird, it says, yeah, for instance, um, chemistry was gonna hire for this fall and that got scratched because I guess they hadn't gotten to that point. It says a teaching track math position for which the search committee has completed the work is under negotiations. I think that could use some clarifying.
Yeah.
Um, um, sorry. Um, okay. Okay. That's- So, okay, so that illustrates the quadratic conversions that we have here. Now, um, now, another perspective on this QR iteration is related to the power method. I think all this, everything I'm doing here, moved from the power method, various steps. Gotta make sure I'm still pointing the same way. Whoops. Okay. All right. So we have, so I have, H. My subscript straight. I'm not gonna put subscripts and everything, in case what's happening from one iteration to the next. All right, so, because we're gonna shift varying from each iteration. So HK shifted is pure factored into QKRK. And then the next essence or matrix comes from multiplying those in reverse order. And adding shift back. So then, if I define QK hat to be the accumulation of all of these Qs, so many Givens rotations, and then RK hat is product of all of these Rs, but in the opposite order. That it can be shown, kind of pain, that this is equal to this polynomial of H1. So notice it needs to be linear factors. If you multiply together. The shift is different every time, but we still consistently have H1. Okay. All right. Now, or put another way, just rearranging this, I have products. Okay, so now I have that. Okay. Now, but what does this mean? Oh, okay. Okay, ooh, this is getting interesting. Dr. Casabos did not respond to me, but I guess he's in a meeting, but Sharon did, and said that Sarah was a verbal offer. That position should be okay, but the other position is, quote, under negotiation. So that one might get scratched. Yeesh.
It's very hard. A lot of times people want to keep negotiating to get more money, and that might have been,
Would have, yeah, so. Okay. Well, because the last I knew, all the offer info was forwarded to the dean's office, who would send the formal offer letter. And she was still waiting for it.
ooh. Man, that's already a nerve-wracking situation. That's adding more to that.
Yeah. So, dang it.
Anxiety that would come with that.
Yeah. I guess, the thing is, just this past year, it just started just this one time. In fact, the cost of living increase because, we have all this inflation and stuff. And I thought, well, nice if that could be a yearly thing because cost of living keeps increasing. No. But nice idea. Okay, so to interpret what's happening here, that says that the columns of UK hat come from K iterations of what is called inverse iteration. Applied to H1, or really H1 transpose, but H1 transpose is the same eigenvalues as H1. Okay. Both shifts. U1, U2, and so on, up to mu K. Now, I need to tell you what inverse iteration is. Inverse iteration equals the power method but power method is when you keep multiplying by A. Inverse iteration is a power method applied not to A, but A minus mu identity inverse. So in other words, you keep multiplying some initial guess by that. Now, whereas power method gives you the largest eigenvalue of A. Inverse iteration would give you the largest eigenvalue of this matrix. But the eigenvalues of this matrix are 1 over lambda minus mu. So it gives you the eigenvalue that is closest to mu, because that will make the denominator smallest to the overall fraction largest. Dang it. And what should be happening is these shifts ought to be converging to an eigenvalue. Okay. And the thing is, this inverse iteration converges rapidly if your shift mu is closer to an eigenvalue. And if we're doing a single shift strategy, which it is converging to an eigenvalue, then this iteration should converge rapidly. Yeah, it's because we're closer to an eigenvalue. And that will lead to a most rapid conversion. Okay. Unfortunately, I spent too much time on this. I may not have enough time for the good part. Okay. All right. Because what I just described to you up to this point is really all we need if we know that A has only real eigenvalues. Okay, so this single shift strategy does not work well if A has complex eigenvalues. Because when that happens, your shift is real, but we're choosing it now. If you have complex eigenvalues, there's no way that any mu you could choose to be H and N, it's not going to approximate an eigenvalue well. It will not converge to a complex eigenvalue. So you won't get good convergence. So what we can try instead is double shift. If we let mu1 and mu2 be the complex eigenvalues of the lower right 2x2 block. So if we determine, and that's not hard to determine, that this lower right 2x2 block of H has complex eigenvalues, we can go ahead and compute those two complex eigenvalues without any trouble. And then we proceed in the similar manner as before, just using these two shifts for the next two iterations. So we shift by a complex eigenvalue. And now our QR factors will be complex, even though H is real. And then we proceed as before, put the shift back. And then we use the other complex shift on H1 with a second QR factorization. Whoops. The third step should be QR, not RQ. All right, so we could just do that. And that does help the situation in terms of ensuring more rapid convergence. So you might think, okay, now we're done. But we're not, because all this will involve complex arithmetic. So we don't want to do that. Okay. I mean, if H is real, chances are whatever imaginary parts you would get from all this would cancel out. But as a rounding error, you're still going to have an imaginary part. And then you'll be dealing with complex arithmetic from this point on. So that'll slow down your algorithm by a factor of like 3 or 4. Okay. Now, well, here's what we can do. All right, so the point it's bad because it's slow than real arithmetic. Okay. So now we'll try instead what's called the double implicit shift strategy. And we don't want to use these shifts, but in a way that avoids complex arithmetic. So, okay, so you can show that if I define this matrix M to be H minus mu2 identity, H minus mu1 identity, and I multiply it all out, then we have H squared minus mu1 plus mu2 H plus mu1 mu2 identity. And these quantities, even though they involve complex numbers, they're real. Like if I let mu1 equal A plus BI, mu2 is A, yeah, minus BI, because they're conjugates. So this is equal to 2A, and mu1, mu2 is equal to A squared plus B squared. So everything you see here is real. It also show that this is equal to, this matrix M is equal to Q1, Q2 times R2, R1. And if I label this, call it C, and I call this R, this is still a QR factorization. The product of orthogonal matrices are orthogonal, product of upper triangular is upper triangular. But M is real. And you can take a QR, if you take a real matrix and you QR factorize it, the QR factors are going to be real. So Z and R are real. Even though Q1, Q2, R1, R2 individually are complex. what else I can show, and as I'm delegating a lot to the notes, so you can see the full algebraic steps there. It can be shown that the output of this double shift strategy, H2, by working backwards through these steps and making a lot of substitutions and just out and out algebraic trickery, you can show that this is equal to Q1, Q2 transpose the original H times Q1, Q2. But I've labeled Q1, Q2 as Z, so it's V transpose HZ. So this means we have a way, because our goal is to get from H to H2. Whatever happens in between, we don't care as long as, number one, we want to make it efficient, and we also want to avoid complex arithmetic. But now we have a relationship between H2 and H that involves only a real matrix. So here's what we can do now. New approach to carrying out this double shift strategy. First, go ahead and compute M. And M would be H squared minus 2AH plus H squared plus B squared. And then where A and B are the real imaginary parts that I wrote down earlier of your two complex shifts. And everything here is real. Then compute the QR factorization of M. And whatever Gibbons rotations you needed to form Z, you can now apply those on both sides of H. So H is Hessenberg, H2 is Hessenberg. So all of this is pretty efficient. Okay. So this avoids complex arithmetic and we get to rapid convergence. So I think, okay, now are we done? Of course not. Because computing H squared, this is order n cubed plus. We're trying to keep our iterations down to order n squared work. So squaring H is a deal breaker. Everything else that I've described is reasonably efficient. But that one part messes it up. What? Sorry, what? It's these. Wait. Oh, that's transpose. Yeah. Whoops. Yeah, that would not preserve eigenvalues. Okay. Okay. Last page. Okay. So what's going to save us is something I brought up last time. This is the genius of John Francis here. The implicit Q theorem for rescue. Okay, so here's what we do instead. We don't form M entirely. We only form the first column of M. Okay. That'll be our first step. Now, if we're taking a second degree polynomial of a Hessenberg matrix, that column is only going to have the first 3 entries be non-zero. So it'll take very little work to do that. Okay. Then we will form a householder matrix, which I'll call P0. So that if you apply it to this first column of M, it'll zero everything below the subdiagonal. Now, the reason we're doing that is this P0, this is the first transformation of QR factorizing the M we're not going to form. So, because how do you normally QR factorize? You can form M and then you do all these householder reflections to zero out all subdiagonal entries. So this is the first one. So we only start the process. And it turns out that's going to be enough. Okay. Then what we do is we apply that householder to H. P0 transpose HP0. This is the first step of what we really want to do. H2 is the transpose HC. So again, we get the ball rolling. Now H is Hessenberg. Applying this household reflection on both sides makes it no longer Hessenberg. So then what we do is we apply more household reflections. To this matrix that we got last step, with the goal to make it Hessenberg again. Okay. All right.
Would it always restore to Hessenberg form?
Well, and we can choose whatever householders we need.
We're choosing to.
Yeah. Because I haven't said how these P's don't necessarily relate to anything over here.
Okay.
They're just whatever it takes to Hessenberg it.
Okay.
Yeah. Okay. Now, but the thing is, why this is all we need? That these other householders, starting from P1, they don't affect the first row. Or column of whatever matrix are being applied to. Because their goal is to make something Hessenberg. Like, so for instance, if you're trying to make a matrix Hessenberg, you work in the first column, you're gonna use the second row on down. You don't have to touch the first row. So what that means is, if I define a matrix called Z tilde, which is the product of all of these householders, including P0. Okay. Oh, I goofed here. I stop at n-2, not n-1, because I'm trying for Hessenberg, not upper triangular. Okay. Yeah. Yeah, but when you're making a Hessenberg, you don't have to touch the last two columns. But yeah. So if I define Z tilde to be the product of all of these, then this matrix has the same first column as the matrix Z that we're unable to efficiently compute. So it's because both Z tilde and Z have the same first transform, P0. And then all subsequent transforms whether these that we came up with or the unknown remaining transformations in Z, they would not touch the first row or column. So we don't know Z, we'll never know Z, but we do know they have the same first column because they both start out the same way. So by the implicit Q theorem, Z and Z tilde are essentially equal. Okay. And if I call H2 tilde the Hessenberg matrix we got from doing all this, then H2 tilde is essentially equal to the matrix H2 that we originally wanted. The entries would only differ by sign. So in absolute value, they are equal. That's a O, not a P. Yeah. Looked like I was writing spare. It's like, no, so are. Okay. So now we're done. And everything that I described here, well, okay. This last procedure is called a Francis QR step. Okay. So that's the procedure that works. So you can do single real shifts or double complex shifts without doing complex arithmetic, all reasonable efficiency, and we get the very rapid convergence that these kind of shifts produce. Okay. So this whole procedure is order n squared floating point operations, and this takes hardly anything. This is order 1 operations. And then here it's working on a single vector to get P0. So it takes only order n to get each one of these P's, and then actually applying them. Okay, for a okay. Well, what's happening here is since this matrix, it's no longer Hessenberg, but it's almost Hessenberg. So making it Hessenberg, because Hessenberg reduction in general is order n cubed process. But when the matrix is almost Hessenberg to begin with, you have like at most one non-zero entry below the diagonal to get rid of. So each of those householders can be applied efficiently, or you might be able to get away with givens because there's so little work to do. Okay. Right. So are there any questions about this rather strange process?
Apply P1, P2 up to Pn to that whole matrix.
Yeah.
So for example, if I'm applying P3.
Yeah.
I'm going to apply it on both sides.
That's to both sides, yeah. Yep. That to be a similar transformation. Okay. Right. So that's why we're in trouble with having the implicit Q theorem. Turned out to be what saved the day. So I guess the very early instance, this is from like the late 50s, early 60s, of fake it until you make it. That's what we're doing. We're faking a QR factorization. So starting it out in the right way, and it turns out that that's all we need. Okay. So just wrap up. Anything of relevance here? Oh, I hate uncertainty. Dr. Kasopoulos responded to me and he said, Sarah's offer stands as far as I know. The second is the one he's not sure about. All right. Last few factoids we have here. Okay. Oh, yeah, so some more specifics about efficiency. That a Francis QR step takes roughly 10 n squared flops. Okay. That's if you're only after the eigenvalues. It takes 10 n squared more if you also go to the trouble of accumulating all the transformations. In other words, if you want the entire real Shor form, you have to think about, okay, do you only want the eigenvalues? Or do you want the entire Shor decomposition? Because if you only want the eigenvalues, you just care about getting A to this quasi-hypertriangular form. And once you apply the orthogonal transformation, you can forget about it. But if you want to accumulate all of them and get that matrix Q, like, Q, T, Q transpose, then that's an extra cost. Okay. Okay, now the entire QR algorithm. So all iterations necessary to reduce to this real Shor form is roughly 10 n cubed. Well, so a lot more expensive than Gaussian elimination, which is only 2/3 n cubed. Okay, and that's for eigenvalues only. You have to incur 15 n cubed more. If you want the Q in the real Shor decomposition. That's why, like, when you call MATLAB's Eig function, what it does depends on the outputs you provide. If you just want a single output, it's going to give you a column vector of the eigenvalues, so it will only incur this cost. But if you call with two outputs, you want the matrix of eigenvectors too, then it's going to be a lot more. Okay, so what you have to do is monitor the subdiagonal of your Hessenberg matrix. For any decoupling opportunities. So basically, the Vennetrian subdiagonal is so small that you can basically declare it to be 0. Then you say, okay, now I'm going to continue on this other block, this sub block of it. That's still unreduced. Okay, yeah. Q transpose of a Shor decomposition. Or we have a real Shor form. Okay.
I was just because it's transpose and it's T and I.
Oh, yeah. That's unfortunate, but yeah. Okay. And that's one of the things that's a key part of efficiency, because I'm saying, okay, Francis QR step takes 10 n squared, but most times you're not incurring, it's not 10 n squared, it's 10 p squared, where p is the size of the unreduced block you're currently working on. So you're actually applying this Francis QR step to smaller and smaller matrices, and that's dramatic. So the most expensive part of QR algorithms up in the beginning, the Hessenberg reduction and the first few Francis QR steps, until you get some decoupling, and then the amount of work per eigenvalue gets less and less. Because otherwise, the total of this would add up to a lot more than 10 n cubed. And then that's just an estimate, because it's iterative method. It's not like Gaussian elimination where you can count the exact number of flops. This is just an estimate based on like how many iterations it typically takes to achieve decoupling. We're assuming real. I mean, it wouldn't really be much different in this complex. Oh yeah, definitely. Yeah, Yeah, but that's where T is truly upper triangular, and Q, it'd be QTQH. Where Q is a unitary matrix that's complex, instead of just a real orthogonal matrix. And I think sorry, I've gone past time, whoops. I haven't actually said anything about how you get eigenvectors, and I won't. Because that's a whole other process when it's unsymmetric, but I will be able to talk about that with the symmetric case, which is coming up next. Okay, sorry to go over. So finally, we have the main algorithm QR.